Okay. Okay, good afternoon, everyone. Whoever is there in the live session.
Good afternoon, sir.
Yes, so I hope Subham Kumar is online, right?
Right, sir.
No, actually, the voice is echoing. My voice is echoing. I have to. Okay, now it is fine, I believe. Subham, are you able to listen to me?
Yes, sir.
Okay. Now, are you getting the echo?
No, sir.
Okay. Okay. Yes, I believe you have asked me some questions, which I no, it is
Sir, I
not
have a
you.
question. Sir, I have a question regarding assignment 10, part B.
Assignment 10.
Yeah, part B, sir.
Okay. Because some persons have asked questions on assignment 10 and 11. Anyway, assignment 10 you are saying, let me check. Assignment 10. Let me open the assignment 10 first for you. Tell me, what question do you have in part B? Yes, Shubham. Okay, meanwhile, I find Prajesh Patel also has joined. Hello, Prajesh.
Hello, sir.
Okay. Yeah, Shubham, what is your question? Tell me. Shubham, are you on the line? Are you online? Shubham. Shubham, you are not audible. I don't know whether you are trying to communicate, but you are not audible. Anyway, I find another couple of persons over here. Himanshu, Priya. Hello, everyone. And let me find who are there in the YouTube. Okay, I don't find anybody in the YouTube. Okay. Anyone else? Rajesh, do you have any specific question?
Yes, sir. Sir, it is regarding optimization. Sir, I don't know the exact assignment, but in some assignment it happened that our optimization do not converge, sir. Though
Okay.
everything we followed up to, as you have done in the video lecture, but though that optimization do not converge, sir. So what kind of error analysis we can do in that?
Okay, I got your point. So let us do one thing. Let us take an example and then try to perform the optimization at my end, and I will show you over there. Okay. So that will be a better way of explaining things. In fact, some of the learners, they have approached me to explain the things in assignment 9 and 11. So I believe assignment 11 has some portion which you can check. So let me open this one first. For Shubham, I opened assignment 10, but he is not responding now. So let me open assignment 11 for everyone. Okay. So here we have assignment
Sir,
11.
sorry to disturb, sir. But sir, can you follow assignment 9, sir? Because in that I got particular error in assignment 9 question.
Okay, then I have to open assignment 9 file for everyone. It will take some time. Let me check assignment 9. Okay, so let us put the assignment 9 over here. Okay, is my screen visible?
Yes, sir, it is visible.
Okay. So let us keep them side by side. So assignment 9, this is the assignment 9. I hope you remember. A counter current heat exchanger with 10 meter square heat transfer area is employed to cool an equimolar mixture of benzene and cumene. The flow rate is given, temperature pressure to 85 degrees centigrade water is used to cool down the hot fluid. Hot fluid passes through the tube bundle. There is no pressure drop across either hot side or cold side. Cooled mixture of benzene and cumene is fed to a Radfrac distillation column. The column details have been given. Use NRTLK method. Use tolerance 001 for all calculation. Okay. So what we have benzene and cumene, equimolar mixture of benzene and cumene, and we also have water, right? So we have three components over here. So we have benzene, cumene, and water, right? And we are asked to use NRTL RK method. So we have selected the method as NRTL RK and we have analyzed it, right? So the results are available. Go to simulation. In the simulation, let us go to the main flow sheet. Here, what it says counter current heat exchanger. So this is the counter current heat exchanger that we have, having 10 meters square heat transfer area, which we will later confirm, employed to cool a equimolar mixture of benzene and cumene. So benzene and cumene, so BC in, this is the one. So let us check BC in. It should be 200 kilomole per hour, 120 degrees centigrade, 2 bar. 200 kilomole per hour, 120 degrees centigrade, 2 bar, and equimolar, 0.5, 0.5, right? So this is BC in, and water flow rate is, okay, water flow rate probably they are asking over here. So water temperature and pressure given 25 degrees centigrade and 1 atmosphere. So let us check water in. Water in is 25 degrees centigrade and 1 atmosphere. Now, although the water flow rate has been asked to calculate, but we do not have any data over here, but until unless we provide some data, it will not go forward with the simulation. So we give a dummy data, say 4 tons per hour, and start the calculation. Later we will converge to the one which is asked. Okay, so this 4 tons per hour is a dummy data that we have given. Now, let us open the heat exchanger, because heat exchanger is this one. I think it is B1, right? Yeah, it is B1. So we open B1 setup. It is having so it is having 10 meters square of heat transfer area, and the water has to be, the benzene and cumene has to be cooled down to 85 degrees centigrade. So this is the hot fluid, water is cold fluid. So hot fluid exit temperature is 85 degrees centigrade, right? So we have put hot stream outlet temperature is 85 degrees centigrade. Okay, and this is a counter current flow, right? Now, at this moment, we are not using 10 meters square heat transfer area, because this information will be needed to us later in order to arrive at the desired water flow rate. Okay, so perhaps we have to tune the water flow rate, which will be requiring 10 meters square of heat transfer area for the heat exchanger. Okay. So this one is done. Hot fluid passes through the tube bundle. So hot fluid passes through the tube bundle that has been given. There is no pressure drop across either hot side or cold side. So pressure drop is 0. So outlet pressure is 2 bar, right? Hot side outlet pressure is 2 bar, because the hot liquid, benzene and cumene, it has the pressure of 2 bar. So hot side pressure is 2 bar, right? So heat exchanger specification has been given. Now, what is said? After that, cooled mixture of benzene and cumene is fed to a rat-frac distillation column. So this is the rat-frac distillation column. So BC in, this is BC out, it is going into the rat-frac column. Okay. And the rat-frac column, it is equilibrium type. So we have given, sorry. Yeah. So this is the rat-frac column. Equilibrium equation type. So it is equilibrium type, 6 stages. It is having 6 stages. Feed above third stage. So we will have this information over here at the stream. Feed above third stage. Reboiler duty has been given 2 megawatt. So configuration, reboiler duty is 2 megawatt, 2000 kilowatt. And then condenser, total condenser is at 1.5 bar. So go to condenser pressure. Pressure is 1.5 bar. Okay. So what else? Reflux ratio is not given, but probably we are having certain information over here, which will ask us to vary the reflux ratio and all. Okay. Let us see why we have given it 0.9. Because reflux ratio is 0.9. Is it given anywhere? Reflux ratio? Maximize mole fraction of benzene by varying molar reflux ratio with a minimal such and such. Okay. Okay. For the time being, let us not bother about the reflux ratio, because right now we have not come to the question number 8. Question number 6 and 7, they are only with the heat exchanger. Okay, they are only with the heat exchanger. So no matter what is there over here, we are not bothered about this portion. We are bothered about only this portion. So let us deactivate this portion. Okay, this entire thing is deactivated. So B3 is deactivated. Don't worry about it. Now, what is asked? It is asked mass flow rate of water used in the heat exchanger is this one. Okay. Now, what should be the criteria of mass flow rate of water used in the heat exchanger? Here, the 10 meter square of heat transfer area is important. So you will use a design spec over here. So in the design spec, what you will do, you will write heat exchanger area. Okay, what is heat exchanger area? It is the block variable calculated heat transfer area in square meter. So this is 10 meters square. What shall we vary? We shall vary the mass flow rate of water used in the heat exchanger. So mass flow rate of water. So we will use vary mass flow rate of water in, because this information was not there with us. We had given a dummy variable of 4 tons per hour. So that one, we have to manipulate the variable between 2 to 6. Okay. So we had given a dummy variable of 4, but we will vary it from 2 to 6. Okay. And what is the specification? Specification is the exchanger area. Exchanger area target is 10, because we have got this information, 10 meters square of heat transfer area, right? And tolerance value is 0.001 because we have used tolerance of 0.001 for all calculations, right? So with that information, let us run this process, okay? So we first initialize and then run. Okay, the results are now available, okay? Now let us see in the design spec. See the results in design spec. You have exchanger area of 10.0009 square meter, for which manipulated variable it is 5816.03 kg per hour. That means 5.816 tons per hour. So it comes within our accepted range. Okay, so this is how we fix the mass flow rate of water used in the heat exchanger, right? Then outlet temperature of water stream is what? What is the outlet temperature of water stream? For that, it is very simple. You have to go to the results of water out. So just go over there, result summary, stream. Yeah, what is water out over here? This one, right? So let us see over here only, water out. The outlet temperature of water is 83.6989. So 83.6. Okay. So that's how we calculate the outlet temperature of the water stream, right? Then we come to the next three questions, 8, 9, and 10. Maximize mole fraction of benzene in the distillate by varying molar reflux ratio with a minimally constraint. Flow rate should be at least 100 kilomole per hour. Answer the following questions. Okay, maximize the mole fraction of benzene in the distillate. So now we have to reactivate this portion. Now this portion is important. Okay, now we reopen this one. These informations are given. Reflux ratio information has not been given. We do not know what should be the reflux ratio, but let us begin with some value, say 0.9. Okay, and all other informations are given already. Pressure, stream temperature, condenser, reboiler. So these are the default values. We are not fixing anything. Now, what needs to be calculated? Maximize the mole fraction of benzene in the distillate by varying molar reflux ratio with a minimality constraint. So for that, we have to close the design spec and open the optimization. So here the optimization routine needs to be opened. So we have to define the benzene in the distillate flow rate. So molar flow rate of, okay, no, it is the mole fraction of benzene in the distillate. So mole fraction of benzene in the distillate. So this is ben mol FR, right? That needs to be maximized. So you are talking about the maximization problem, right, Frajesh? So you are now maximizing ben mol FR, which you have defined over here. But this is not, and by varying molar reflux ratio. So by varying, so this is the vary button. What do you vary? You are varying molar reflux ratio in the B3. B3 is the column, fractionation column. So you are varying between 0.1 and 10. We have taken 0.9 as a dummy variable, but here you will get the exact variable. So you have to vary between 0.1 and 10, right? But here is a catch. There is a minimality constraint of the distillate flow rate. It should be at least 10 kilomole per hour. So the distillate flow rate should not be less than 100 kilomole per hour. So there you have given some objective. So this is the constraint. So you give this constraint over here. So this is the minimality constraint. And you define the constraint over here. So what is that constraint? Constraint says distillate flow rate, stream distillate, molar flow. Okay. So this needs to be, what is the specification? It should be greater than or equal to 100. So your minimality constraint is distillate flow rate should be at least 100 kilomole per hour. So it is should be greater than or equal to 100 with a tolerance of 0.001. So already we have defined over here, take all the tolerance, use tolerance of 0.001 for all calculations. So that's exactly what you are doing. Now all the specifications are fixed. Okay. So now let us reinitialize and then we run the process once again. So it will do the optimization for you and it will give some results. Okay. So the results are available. Now look at the results. What is it asked? The said maximum mole fraction of benzene in the distillate at optimum condition is. So go to the result optimization. Yes. No, sorry. Manipulated variable, right? No, sorry, what is that? Maximum mole fraction of benzene. So maximum mole fraction of benzene is this one. Maximum mole fraction of benzene is 0.958788. So it is 0.958. Okay, we have put it over there. And then molar reflux ratio at optimal condition. What is the molar reflux ratio? Molar reflux ratio is this one. Final value is 0.61231. It is 0.61, right? And heat duty of the condenser at the optimal condition. So you have to find the heat duty of the condenser, right? So you have to go to the results over here and find the condenser. Where is the condenser? Condenser will be here, right? This is the condenser heat duty. So condenser heat duty in kilowatts. So you simply change the unit into kilowatt and you find 1393 minus 1393.58. So minus 1394 we have given. Okay. So this is how we solve assignment 9. Got it, Prajesh?
Yes, sir.
Okay. Okay, so yeah, meanwhile, many people have joined. I think Alekha from IIT Tirupati, Shivraj, Shibi Bharat, Prabirkumar, Aniket, Shaurya, Vania, Aryan, all of you, welcome. Let me see whether they have any question. Priya is saying hello, good afternoon. Good afternoon, Priya. Rajesh, you are asking, sir, if you are on RADFRAC input, it is not reflected on screen. Rajesh, are you having any doubt over there? I think I have explained it. Okay, Shivraj. Shivraj, please continue. Shivraj, you are not audible. Shivraj, you are not audible at all. I'm not able to hear anything. Anyway, 80, who is 80? Alekhya from Tirupati. Alekhya is saying, sir, I'm reproducing one paper related to waste refrigerant separation using ionic liquids. I am getting calculation. Can you please help me with that? First of all, Alekhya, I have not worked with refrigerant or ionic liquids, so I do not know how much I will help. But if you follow the lectures, you will definitely be able to get through. But yes, I mean, if I get your simulation, maybe I can look it once, but unfortunately, I cannot spend much time on that. For that, you need to approach your supervisor. Okay. And until unless I see the simulation, I'll not be able to help you also. That is also one thing. Shivraj is saying, sir, can you please explain how to solve a distillation? How to solve a distillation column? Shivraj, already I have got the video lecture. You have got the video lecture, so you can see how to solve the distillation column. Shaurya is saying, sir, can we do research project under you? Shaurya, actually, I do not take any outside student like that. You have to take admission in IIT Guwahati, then only it is possible. Vacuum distillation column, Shivraj, yeah, vacuum distillation column is not covered in this course. Vacuum distillation column, I have tried to cover in advanced, as far as I remember, I have covered it in advanced Aspen Plus, which is also running parallelly. No, vacuum distillation column is not covered over here in this course. Yeah, Prajesh, you are typing something. Sir, I have one practical simulation problem, don't know how to approach. Can I speak? Yes, you can speak always. This is the forum to speak only. So definitely you can speak.
Sir, it is regarding, actually I am working in a oil and gas industry. So
Okay.
once incident happened in which, sir, there is a LPG loading was occurring at night, and without pump, the line pressure is equal to 11 or 12 kg, sir. in idea means in a isolated, but when tankers are filled, so because of tanker are having low pressure, the line pressure is almost around 10 to 11 kg, though we start the pump, sir. The pump has some differential pressure uh, production, but though we start pump, the line remain on to 10 to 11 kg. So sir, what happened, one TSV is mounted on that line, and it somehow it got passed or maybe leaked, but it was on the set pressure of 23 kg, sir. But our line pressure didn't went above 18 kg. We checked trend and all. So if anyone want to calculate that how much amount of LPG got leaked in maybe 5 minutes or any duration, so how can we simulate this type of questions, sir?
Uh, so anywhere can you measure the flow rate anywhere in the line? Do you
Yes,
have
sir.
any mass flow meter?
Flow rate can be measured, sir. But,
Okay.
sir, they are not of very much accuracy. So we can have, they are not that much accurate, sir, but error of 100 or 200 kg per hour of is normal, sir.
100 kg per hour is a big number, particularly for
Yes, sir, but
gas.
that we are having short capacity instruments, so that's why
Uh,
this error is there, sir.
okay, if you, I mean, offhand, I'm not able to say anything. Maybe if I get to know all the information at one place, I can do a quick calculation, but definitely it is possible. But as you can see, this is only for steady state calculation. You have to put the pipeline in place, and you have to take certain assumptions in your simulation, and you can definitely do it. Yes, but obviously there will be some percentage of error. I do not know whether that error will be of the order of 100 kg per hour or so. But definitely you can try the simulation once. Yes, it is possible to try the simulation. But for that, you have to do the piping properly, because you can see in the Aspen window, there are certain model palette of pressure changers. You have pump, compressor, valve, pipe, pipeline. So all
Sir,
those things.
actually, sir, that loading pipe was of a 6 kg diameter, 6-inch diameter, but that TSV mounted on that line was having a 1 inch diameter. So,
Mhm.
how can we, sir, approach this? Because
No, I didn't get you. Sorry.
sir, the loading line was of a 6-inch diameter, but the TSV from which LPG got leaked, sir, that was of 1 inch diameter. So
That is okay.
can we simulate that 6 inch and 1 inch in
Definitely,
no,
definitely. There
sir, is
should, you
pipe
have to put an,
reducer and
yeah, you have to put an adapter, pipe reducer you have to put. I think those things are also there. You have to, you have to specify how many numbers of pipe reducer, how many numbers of elbow, what are the angles, what is the elevation, all those things you can put in the pipeline. That's what I'm
okay,
saying. I mean, these information are there. Only thing you have to explore, and there will be some error that is expected, but approximately you can always find out without any issue.
okay, sir. Okay, thank you.
Yeah, so
Sir, can you
meanwhile
say
I
the
have
model in which model palette I can find this reducer and
pressure changers. Pressure
all? Okay,
changers.
sir. Okay, sir. Okay.
Okay, Shivraj is saying in assignment 10, I have got the answer, but other answer I didn't get. Okay, fine. I promise that I will explain assignment number 10, which I will do now. Not much time left, but I will still do it. Sir, can we also simulate membrane simulator in Aspen other than the separation? No, membrane simulator is not there, Shivra. Assignment 7. Praveen, these things, sir, by following the video lecture, recent assignment of the question when simulated. Praveen Kumar, you can send me this calculation by email. I can try. Sir, by following the video lectures in recent assignment, the questions when simulated Aspen getting errors. Yesterday assignment for question number 8. Aniket, you have not written the assignment number. What do you mean by yesterday's assignment? Assignment is assignment number 11, question number 4. Okay, a lot of questions are coming in. Okay, I promise somebody that I will cover assignment 10 part B over here. So that I will do. Okay. So I will do it first. Okay, so is my screen visible, everyone? I hope it is visible. Anyone, can you please confirm whether it is visible? Prajesh
Yes, sir.
or Kit?
Yes,
Okay,
sir.
okay, thank you. So this is the problem statement, if you remember, assignment 10. An equimolar binary mixture of benzene toluene is separated by using NMP as the selective solvent in an extractive distillation column. Column condition is given. Name the extractive distillation column as col1. And distillate from col1 is distben. Solvent-rich output for col1 is fed to this column. For solvent recovery, name the DS2 column as col2. Solvent-rich output. Okay. Let us go one by one. So it is equimolar binary mixture of benzene and toluene, and it is separated by NMP, N-methyl 2-pyrrolidone. Okay. So basically we have 3 components over here, benzene, toluene, and NMP. And probably we are asked to use NRTL property method with binary interaction tab using UNIFAC. So we have taken the method NRTL and binary interaction of NRTL. We use estimate using UNIFAC. Okay. So we have ticked over there and we have got some results, right? So go to simulation. Now, in the simulation, there are two things, call 1 and call 2. Okay, this is call 1. Here it is feed. In the feed, we have binary mixture, and this is NMP. And call 1 is extractive distillation column. So let us see what is feed. The feed is 100 kilomole per hour, 25 degrees centigrade, 1 bar, equimolar. This is feed. And NMP is 25 kilomole per hour, 25 degrees centigrade, 1 bar, right? So this is our NMP. Call 1. Let us see this call 1. This is a rad frac column. So this is a rad frac. So it's a rad frac column, 10 stages, solvent fed above 9th stage, solvent fed above 9th stage, NMP is a solvent. And then reflux ratio is 2. So this is the reflux ratio 2. Distillate rate 50 kilomole per hour. Total condenser at 1 bar, right? This is call 1. Distillate from call 1 is dist-ben. So this is the distillate from call 1 is dist-ben. Solvent rich output from call 1 is fed to DSTWU. So this is the solvent rich. This is the solvent rich output. It is fed to DIS2. So, okay, this is call 2, right? Okay, so this is call 2. This is the call 2. So let us open call 2. Yeah, this is DST column, 5 stages. We have 5 stages, light key recovery at 0.99, toluene is light key, heavy key 1 bar, 1%, isn't it? Condenser pressure, column pressure are 1 bar, column pressure 1 bar, and condenser pressure 1 bar. So, column pressure drop is 1 bar. So if the condenser pressure is 1 bar and column pressure drop is 1 bar, then reboiler pressure has to be 2 bar, right? So if it is 2 bar and it is 1 bar, then only the column pressure drop will be 1 bar. So that's how the condenser and reboiler have been fixed. Okay, so solvent recovery is done. This is column 2, and the solvent rich output from the call 2 is named RIC-Sol. This is a recycled stuff. So this RIC-Sol, this is solvent rich, and this solvent rich thing is So this is the solvent-rich one. 50% of the Rexol after bringing it to the fresh solvent temperature pressure condition. So 50. So there is a splitter which splits it to 50%. Okay. So 50% of Rexol after bringing it to the fresh solvent's temperature pressure condition. So this is 25 degrees centigrade 1 bar. So here also we will put a cooler because it is very hot. So we put it at 25 degrees centigrade 1 bar so that it comes at the solvent condition. And this S9 Rexol, we are sending it to column 1. Okay, is recycled back to the column 1 at the same stage as that of fresh solvent feed. So both of them are at stage number 9. Okay. Name the recycled stream as recyc. Okay, so this is the recyc. Use inertial property method. Okay, answer should be correct. Feed stage of column 1 is selected in such a way that the benzene mole fraction is Dist-Ben is maximum, right? Feed stage. Now, remember when we were talking about col 1, we didn't say anything about the feed stage. This feed stage was given a dummy variable because we have to somehow put some values over there, otherwise the simulation will not run, right? But this feed stage is selected such a way that the benzene mole fraction in Dist-Ben is maximum. Benzene mole fraction in Dist-Ben. So this Dist-Ben benzene mole fraction has to be maximum. So that is the condition. For that, we will use a design spec, right? So for that, we'll use a design spec. So here, what is mole tall? This is dist tall, stream distol. Okay, not this one. Perhaps, how many design specs are there? Only one? It should be benzene, right? So okay, maybe we have done over here. No, not this one. Okay, it is said maximum, so probably we are using optimization. Are we using optimization? No, it is not that. This one, 6. Okay, sensitivity 6. So what it does, it begins the starting point at 2 because column 1 is the condenser and column 9 is the point where the solvent is fed, right? So feed stage should be somewhere between 2 and 9. So 2 to 9. So it begins from 2 to 9 at increment 1. So this is the feed stage. Okay, so where the feed stage is put. Okay, so this we have to vary, and we will define MF bench. What is MF bench? The mole fraction of benzene is in dist bench. Mole fraction of benzene in dist bench. And we will tabulate it in MF bench. Okay, so we'll tabulate it. So what we will do, we have deactivated this. We will deactivate this one also because this is not needed. We'll deactivate, but Q6 will activate. Okay, and let us reset and run. So let us run it. Yeah. Now results are available. Now see the result. Feed stage of column is selected such a way that the benzene mole fraction is maximum. So let us see where it is maximum. It is 0.85, 0.9, 0.92, 93, 93, 92. So between 5 and 6, this one is maximum, right? It is 0.9359. So this is the maximum. So 5, stage number 5 is maximum. Okay, so this is the answer. And mole fraction of NMP in the Rexol. So mole fraction of NMP in Rexol. For that, let us go to the result summary. Streams. Rexol. Mole fraction of NMP. It is 0.99041. 0.990. Flow rate of fresh solvent, which gives 93% recovery of toluene. So flow rate of fresh solvent. Fresh solvent means NMP, right? So what it does, let us now we can deactivate it. Mole recover flow rate of fresh solvent, right? So let us see where it has been given. I think this one. Recovery of toluene. No, this is not the one. Is it the one? Q10? No, not this one. Optimization. But 93% of toluene. It should be any one of them, right? We had. This is recovery, no? 93%, right? It is 93% with tolerance of 1.005. So this is the tolerance. And what we are varying? We are varying the flow rate of fresh solvent. So NMP is the fresh solvent. We are varying its molar flow rate between 10 to 100, and which gives 93% of recovery. So here we are defining two things. One is mole tol, mole feed, and recovery. So recovery is, what is recovery? Recovery, we have kept a Fortran code. This recovery is mole tol by mole feed. What is maltol? Maltol is distol. What is distol? Here is the distol, right? Distol, the toluene in distol by toluene in feed. So whatever toluene has been given in feed and whatever toluene has been recovered from here. So this by this should be 93%. So that's what it says. So in quote unquote, we have written maltol by mole feed is recovery, and that recovery should be 93% with a tolerance of this. And we can vary the fresh feed flow rate, right? So again, we have, okay, that we have to Q8, right? Q8, we activate, reset, and we run. Okay, so go to the results and check the result. So the manipulated variable is 55.7048. So the answer is 55.7. So 6, 7, 8 I have done. In the similar manner, 9 and 10 we have to do. Okay. So this is how we have to solve the assignment 10. I think it is already 2 minutes past 4. So we have to end this session. Aniket, you are asking for assignment 11. We do not have any time for that. So let us, if you want, I can take another session for this, but it will be offline outside the NPTEL domain. I will offer another lab session for you. So unfortunately, we have to end today's lecture over here. Okay. So NPTEL, kindly end this session.
Thank you, sir.
NPTEL, you can close this session, please. Okay.
Yes, sir. Thank you for session.